Welcome to lecture 18. We'll continue our discussion on decoding algorithms for the prominent codes that we have studied, and today the focus will be decoding the Reed-Muller code. So let's quickly recap what's the Reed-Muller code. Muller code. There's a finite bit F. Size Q. And it's the ambient dimension. R, which is the degree of the polynomial. Again, for Rn Q MR. Basically, you take all possible polynomials over the speed of degree at most R and n variables. And evaluate this. Use the evaluation of the polynomial on the entire set. That's the reason. Yeah, that was my next point. So Reed-Muller, you can, there's a slightly more general version, which the evaluation is on a product set. Set of the form S power n. Not the entire field of RM, but on a product set. You can study these. So distance Schwartz-Zippel also holds good on this. Things, therefore, these are also a code. The evaluation on this is also a good code. Fortunately, there are not good algorithms till very recently for this unique decoding. It's only as recently as 2016, I think, we had a unique decoding algorithm that worked for the general setting of this for n. And yeah, in fact, I think one paper with Ashutosh in this one, and we have a joint paper that Prahladh talks about it, why these product sets are more difficult than the other. You'll see the proofs that we will study today. When you look at the entire tree, they will use various symmetry properties that the evaluation set has in order to undo the underlying decoding process. Well, if you know the distance is true even for them. So I'll return to ask you this question again at the end of the lecture. I'll return to questions over there. The open questions which are there for general SDFI sets. Today, we'll only focus when yeses. So let's recall a couple of ones. So the block length of this is exactly f to the m, size of f to the m, therefore that's q to the m. The dimension of the code, is referred to as kq in R, is what? Is exactly the number of monomials of this particular choice. So it's the number of E1, E2, EM, such that this 0 is less than or equal to EI is less than or equal to Q minus 1. They can't be more than this. The EIs are integers, and the sum of the EIs should be at most 1. It's this. This is not a, there are not very nice forms for this expression. There are some special cases, for example, when R is less than Q, then we saw that KQ MR is just M plus R choose R. When Q equals to, there is The one is a large field. The field is so large that it's larger than the degree, then it's that. When the field is the other extreme, the field is small, it's the binary field A2 MR. This was M choose less than or equal to R. Otherwise, it depends on Q. So about this one, then about distance. The distance was given by the Schwartz-Zippel Lemma. What was the Schwartz-Zippel Lemma? Let's state it in its most general. Schwartz-Zippel Lemma states that let P be a polynomial in f to the x1 to xn. A polynomial of degree at most r. P is not identically 0. And suppose then we are interested in what's the probability that if you pick a random alpha in f to the m, P of alpha is 0. For example, was the fact that this is quantity is less than or equal to 1 by q power a into 1 minus b by q, where what are a and b? You write r as q minus 1 times a plus b, where and 0 less than or equal to p less than q minus 1. You sort of divided by q minus 1, write it as the question, get that a and b, and you plug that in. That's what's worth. We have stated this without proof. This will give us the distance of the Reed-Muller code, delta, the fractional distance. The fractional distance of Reed-Muller code, delta Q, and R will be this quantity 1 by Q per A, 1 minus P by Q, and the actual distance will be this multiplied by Q per M. So that will be what? That will be Q minus B into Q power M minus A minus 1. So that's the you can check one today. Okay, notice this. What is distance? So what the algorithm which you want to design is if something is less than half this quantity. If the number of errors is less than half this quantity, you want to be able to write it. So that is unique decoding question. So the unique decoding question. That's good. In general, the decoding question. The decoding question for Reed-Muller is decoding problem. So given f given a function f on the whole space, yeah, and other parameter, find all polynomials p in f less than or equal to r x1 to xm, such that distance between f and p is less than or equal to e. That's the problem we came for. And the unique decoding setting is when E is less than delta Q MR by we want to solve the problem. Actually, we'll actually see three different algorithms, each of different merit to it. So today we'll see three algorithms for this problem. The first will be Reed's. This is actually the reason why it's Reed is included in it. It's called Reed-Muller code, Reed's majority decoder. Historically, I think Muller defined the code and Reed gave a decoding. So this is only for the setting and Q equals 2. This will work only for the setting Q equals 2. Then we give a nice local unit decoder. Which will work for all Q, but it will not go all the way to half the median distance. It will be much smaller than, so the E is significantly smaller than delta Q MR vector. It won't work all the way. It will recover a large fraction for us, but not all the way up to half. And the third one, hopefully I have time to do all of them, will actually be reduction to Reed-Solomon. This is due to Pellikaan-Wu. Actually, not that, only 2004. And the reduction will be such a clean reduction that in one shot it will not just solve the unity, it will solve the unity. It will, anything that Reed-Solomon has, it will just inherit all the corresponding decoding. So if Reed-Solomon has a unity decoder, it will inherit the unity decoder. If Reed-Solomon has a list decoder, it will inherit the list decoder. So in some sense, 3 will completely solve the problem for us. But the reason why I could sometimes 1 and 2 are preferable. 1 and 2 will be, as we will see, they will be what I will call local algorithms, whereas 3 will be a more global algorithm. And we'll see what's the difference between 1. But somehow the way they try to handle the input will be more local, 1 and 2, 3 will be global. So let's start off with Reed's majority. Only for Reed-Muller over the binary feed and R. And thing to notice over here, so here we have delta 2 MR that has very nice form 2 to the M minus R. That's the reduced that with the green thing. So if the number of errors is less than half this quantity, we want to be able to decode. So this is going to hand it off. It's going to be unique decoder. The unique decoder. Back towards B. If E is less than delta 2 MR by 2. So what's the setting over here? We are as before let's play a little bit around. So let's any polynomial p of x1 to xn. We can write it in the monomial cases. So what's the monomial cases? You can write it as summation over all s. These are all possible coefficients. These are s is a subset of m. Mod s is less than or equal to r. It's sum ps times phi xi eigen's. And because this guy is we're going to use this term very often, I'll just call this xs, a short for this way. I should actually put it explicitly. We'll call it xs. That's the exponent, so it's C. So in other words, this is summation S, S is an M, mod S less than equal to R, yes. That's the point. Yes. So we given the received word yes, we are promised that it's not too far away from a polynomial because it's less than half the minimum distance that polynomial is unique, and we want to extract P. And extracting P is the same as extracting all these coefficients Ps. So what we would like to do is try to extract the coefficients out of the polynomial. So let's recall some nice facts about these. So suppose I'm working with x n. Let's leave it express it. So suppose x, let's look at xs, and I sum this, but I evaluate. And I evaluate this polynomial on all points in f to the n. What is this going to be? You follow my an f2 to the n. What will this be? Huh? 0, except for one thing. No, empty it will be, I have to repeat it 2 to the n times. Each time it's 1, 1, 1, 1, 1, so that will be 0. When I S is entire monomial, x1, x2, xm, there's only one point where it is 1, everywhere else it's 0. So, because this was 1, if S is m and 0 otherwise. So people, this is the crucial fact. This is basically entire all of the Reed-Muller majority decoder is going to hinge on this. So based on this, let's see the following proposition. Now, so let's look at, let P be some polynomial of degree at most R, but over n variables. Okay. And S is some subset of M, and S is of size R. So there is S is a particular R size. So S corresponds to a particular monomial. Now let's look at what happens, and let B be any string of length m minus R.
That is in F2 or even as R.
Huh?
B in F2.
So for m minus R. M minus R. So it's some m minus R length string. So what we want to do? Let's look at this quantity. Let's look at summation of PA. So A is all points in F2 to the n, subject to A when you restrict it to S bar. So the complement of S, that's an m minus R string, that should be B. So just basically in the complement of S, you fill B, and in S part, you go over all possibilities. So all the summation is a 2 power R. It has an arity of 2 power R. What is this? I just want to ask what this object is. So let's pair this a little bit. So let's define this polynomial. Now this, because it's ranging over V, you can look at the restricted polynomial PB. I'm going to define, so let's just to understand this, let's define the polynomial PB in F less than or equal to R, x1, x2, xr, which is basically PB of A is just P of A comma. And what do I mean by that? I mean in the S location put A, in the B locations put this one. So we actually, this is not an arbitrary thing, but what I mean is in the so I'm not formally defining this. On the S location, I put A. On the S complement location, I put a B. I define the polynomial as this. Okay. Now let's look at PB of. Let me put this upstairs. So PB of X is some polynomial. Let's look at its polynomial expansion. So there was a polynomial expansion for P. P had some polynomial expansion. P of X had some polynomial expansion. It was of the form yes, mod S is the subset of, sorry. It went over all subsets of size n, but because it was a degree R polynomial, you went only over subsets of size at most R. It was ES times the corresponding monomial Xs. Now using this, what will PB of X be? I'm setting various values. I just want to ask one particular. So monomial by monomial will get simplified because in each monomial, some of the expressions are going to be set by P. With excess, let's take and reusing S for two different things. So let's call this P. Yes, S is that specific set over there. This is the general T. So when T happens to be S, does it get reduced? No. So notice that this will PS X bar S will survive. What will happen? Look at any other monomial. Will they get reduced? No. They could have some elements from the first, the coordinates in S. For example, T could be a subset of this particular S, so it will not reduce at all. T will basically each T will get replaced to T intersection S will become the new guy. Two T's which share the same T intersection S will actually sum up. So in fact, what will happen will be this. This will be plus you'll go summation over all T's T subset of yes. You have xt, and this xt will go over all u's, u subset of 1 to m. U formally it will be this. Mod u is less than or equal to r. U intersection s will have to be equal to t. All those u's will add up together to give the coefficient of this particular exponent. And not just they will add up, you'll also have to put b power u over there. Because they will not only add up, you'll have to put that. They will collect the b terms in them. So b power not this, it will be u minus t or s is doesn't matter. So this is what it is. Okay. But notice each one of them, they will all, the only thing I want to notice, okay, that's the formally what it will be. But each of these keys, can any of them be of size R? They will all be of size strictly smaller than R. So in particular, this guy will exactly be p power s, x power s plus summation over some p subsets of s mod p is strictly less than r, I don't care what this x power t, some c. But now so
You can just say that side of t less than side of s only.
yeah, the r is the size of s.
Oh.
R is the size of s. R is the size of s. So what? So PA. So we had this. You were going over f2 to the m. A restricted to s complement is b. Notice that this is just PBA. A going over f2 to the m minus r. Now what happens if I sum this? So recall this fact. If the whole monomial will sum to 1, everything else will sum to 0. So here, you just get PS. Do people see it? Because we are now reduced. So let's recall. Let's see why this fact is. So look at this fact. If it's a complete monomial, if you are working over an m variate space, it's a complete monomial. When you sum it up over the space, over all evaluations of that monomial over the space, you get 1. Any other monomial, when you sum it up, you get 0. So now I have reduced this problem in which it's a, sorry, this is not n minus r, this is you're ranging over an R variate space, and you're ranging over an R variate space. These are the things considered. Every monomial except the complete full R monomial will vanish when you evaluate the whole space. The only thing that's available, and it has a coefficient PFS here. So, in other words, if you look at what is this is a particular subcube of the entire space. If you sum up all of this elements in this subspace of the polynomial, you are getting the coefficient PFS. So PFS is, so from the evaluation polynomial, I'm stating that this is like a subcube of the evaluation polynomial. It's a particular subcube. It's a subcube in which I'm fixing x complement to be p, and then just summing up everything within this. If I sum up what the evaluation of polynomial within this, I get PFS. So this is a way of extracting PFS from the evaluation table. So let's stare at this a little more. So let's look at the end. Let's look at the entire space. So let's think of this as F2 to the M, the entire space. This space is going to get stratified into several this one's based on which B. So this is B being the all zero string, B being the all one. There are totally 2 power n minus r such things. And each of these things, each of these subcubes, when you sum them up within it, you know you will get here. Yes. So there are 2 power n minus r different ways in which you can get PS. Now, what is the number of errors that was? Notice if there's an error in even one of the chunks had no error in it, that chunk will give you the right. There are errors also. So you don't have P with us now, you have F. You have F. So we don't have access to P. We are going to use F. You're going to sum up over F instead rather than P to get this. But if F and P were erroneous, if F was erroneous at a particular point, then this one. So if you happen to lay your hands on one subcube in which there is no error, then F and P are identical on that. Therefore, when you extract this PFS, you get the right PFS. Now, how many errors are there? How many errors do we know? We know this is less than 2. Therefore, at most, even if you had the errors were distributed across all of them, it could affect only strictly less than half the number of. So more than half the number of guys are actually going to be completely error free. So this tells you this one, just compute it for all the blocks, take the majority. The majority value has to be the right value because the errors can happen only in less than minus r by 2. The majority, so at least you can extract P of S. Okay. So I now claim at this point of time, you can extract, if you have a degree R polynomial, you can extract every possible P of S for S being of size R. Because you will choose appropriate subgroup, you will appropriate subgroup and do that. So now you, at the end of this step, you have extracted all the, if the number of errors is so much, all I'm claiming, at most, what I'm saying is PS can be extracted from the subcube. Let's call it SB, which is set of all S going to A, S complement going to B, for all A's in F2 to the R, for any B in F2 to the N minus R. Since E is less than 2 for N minus R by 2, at most, or rather strictly less, at most E, which is less than 2 for N minus R minus 1 subcubes can have errors. Hence, the majority of the subcubes are correct. That's the end of stuff. So at the end of this, we will be able to extract all the degree R coefficients of the polynomial. How do you then proceed? Huh? No, but the lower degrees you don't. For this proposition to be true, it was important that P was a degree R polynomial. If P was strictly degree greater than R, this would, by the way, this is 0. This is PS. That's how the propagation which connect each other. This proposition.
This PSX is the only term which is.
Yeah. Otherwise, if I had done this, if the P was of degree larger than R, this decompose. This fact will not be true. This will X bar F will have more terms sitting. But on the other hand, now that we know all the degree R, you have got them exactly. You can shape them. You can look at this new polynomial, which is just composed of the degree R terms, shave it off from the received word completely. Get a new received word, which so now the received word is close to a degree R minus 1 polynomial, and just keep doing this experiment over and over. So is that clear? So let me write it formally. So can extract all the degree R coefficient exactly. So there's no error now. Using above method. Shave the homogeneous degree R component. From the is from the received word. Yes, and that's the entire thing. And just formally write down the algorithm for the majority decoder there. You are given an F from F to M to F2 such that there exists a P in F less than or equal to R x1, x2, x3 and get that P this number of errors. This is less than 2 to the power n minus R. What algorithm? First step initialize, we set. So we're going to extract the homogeneous component one after another. We will start off with the highest homogeneous component. We will set P to be R. We will set the current received polynomial to be F. This will keep changing as we go, and the polynomial which we have extracted, P is going to be the polynomial we extract. We will start off with 0 and we are going to collect coefficients. How is it going to go? So while P greater than or equal to 0, so while P greater than 0, do the following. What do you do for each S in M? Such that size of S is T. We set PS to be the majority over all B's of F2 M minus T of what? Of the summation over all A's in F2 M such that A as complement is B of FT, in which S is getting replaced by A and S complement is getting replaced by A. Sorry, A. I don't know. Do that, then update PT. PT is now, sorry, not P, just update P. The polynomial is the original polynomial you have so far plus PS excess. You update this. You do this for, so that's the for loop. Then the while loop will come again. We now decrement T. But then before you go to the second step of the while loop, you will have to update FT. The new FT for now will be the old FT minus 1 minus summation over all the old FT plus 1, sorry, FT plus 1, summation over all S mod S is of size T plus 1, ES excess evaluated. You follow what I mean. You just shape at point by point. You go and come up with this polynomial, and you go and you do this. That's the end of it. And then you come out of the while loop and your output. Is the algorithm clear? This is. It's a fairly straightforward algorithm. It's just, and why do I call this local? It's sort of local in the sense that to get a particular PS, you don't have to look at the whole input. You're just looking at one strip of the input, doing it. First, then you're doing a majority. But it's a sort of a, you're stating that the information that I want to recover from, for that, each axis is it's locally you can get it out of some piece of information. Of course, then you also put all these local things together in a global fashion. But each PS is extracted, each PS is sort of extracted locally, and then there's some probability that it might be correct or not. You know, it's slightly probability more than half it is correct. Hence, you have to look at all of this. So there is some local component of each PS is a function of a small part of the input, not the entire part of the input. Whereas the algorithm which we had seen previously, the Reed-Solomon decoder, they take the whole input, play around with it and do it. Here, each PS I get it out of thing. Of course, then I have to do a majority function which involves everything. But there is some local component. That's why they slightly differ. The local global is sort of, it's not a formal distinction between them, but I'm using the fact that I can extract, if the thing was correct, I can extract this from a very small part of the input.
But for example, when you iterate it, P becomes 1.
No. So, when P becomes 1, you are looking at Q. You are looking at larger and larger and larger. So this is not that local. The next one will be an extremely local object. The next algorithm. By the way, this works only for this is very nice for Q being 2. It doesn't extend very nicely to larger fields.
Because
that identity, we don't have such a clean identity in the larger fields. It's not just we have this fact, this fact is a nice fact even in the large field, but the point is when once you go to a large field, here when you're looking at an R-variate polynomial, there's exactly one monomial of degree R, which is the full monomial. That's no longer true even at F3, when GF3. There are several monomials of degree R of the full degree. Yeah, you'll have this complication. So it won't come out very nice. You can try doing this for it. What we will instead do is we will see another algorithm. We see a completely different algorithm, which will work for all fields, but it will not go all the way up to half the minimum distance. So the second algorithm, all fields. And here, what are we going to do? So we are looking at the pair of something. So let's look at this FQ to the M. Now, what we will try to decode is we're going to do a second algorithm, which is going to recover forget. What I will now do is I will not recover the polynomial coefficient by coefficient. I will recover the evaluation of the polynomial correctly on the whole space. And then you can, once you do that, then you can do interpolation to recover the coefficient. So what we'll do, previously we recovered coefficient, we extracted that from the space. Now I will just extract a particular, we'll extract the location at every, we'll extract the evaluation of the polynomial at every location correctly using the erroneous data. And then once you have done that, you can sort of run a interpolation to correct it. So suppose we have a particular point say Z. So Z is a particular point in FQ. And we also know that there's a small patch of corrupted location. These locations, the evaluation of the polynomial that we've been given an F. This is our F. And the delta F of P is less than is equal to E, which is significantly smaller than delta Q M R by P. We will find out what that significantly smaller is. It's something, and that places where the differ is exactly that erroneous location. Now, what I want to do is let's look at a random subspace that passes through this point. So let's look at such a passes through this point. Now, if the subspace was lucky enough that it did not pass through the, if this subspace was small enough that it did not, so the way we first pick a random up some sub. So the idea is going to be the following. The idea is going to be look at the restriction of the function of F or P, both of them, on a random affine space, subspace of dimension R containing the point Z. Okay. So you have this particular point. I'm going to look at random affine subspaces that contain this point. Think of this point as the origin, then it's random linear subspaces that contain this point. Now, I want to say every other, based on the randomness of the affine subspace, this particular point is not a random point, because it's a fixed point in the affine subspace. Every other point in the affine subspace is a uniformly random point as I range the affine subspace over all possible random affine subspaces. Because as I move this affine subspace over the thing, it uniformly covers the entire thing. Every point will get equally, every other point will get equally covered by these affine subspaces. Therefore, every other point, the probability that it's correct or wrong is exactly the fraction of it. So if the affine subspace is small enough, then you can just run a union bound. So what I want to say is, let's look at a random affine space E. All I want to claim is for every, I want to say the distribution of points in A minus E, for random A is the uniform distribution over FQM minus E. The marginal of any point. So once you pick an affine subspace, so you have to be, I'm being a bit sloppy over here when I mean an affine subspace. So the way you have to actually do it is you have to look, you have to do this formally. I'm not, you have to carefully say, what do I mean by an affine, restricting to an affine subspace? I have to say, I want to say I'm picking yes independent affine forms, and I'm writing and I'm looking. So you can sample on all of this. You can do it all of this. No, you can do it. So of course, because it's finite, you can always do it. I want to say there's a much cleaner way of doing it. let me not get into that. I just want, because the main idea is doesn't depend on how you do it. So let's suppose you can do this. This is uniform distribution of. Therefore, but at this point, possibly it's erroneous. This point I have no idea. This is a fixed point. I do not know. Every other, depending on the affines of space, every other point is just as like it's going. The probability that it's going to be erroneous is exactly the fraction of errors because of this fact. Therefore, when I pick an affine of space, the probability that any point there will exist even one point on it that's erroneous will just be the I can just use union form. Therefore, probability. So I'm going to say that. Probability there exists an erroneous point in A minus Z. I will say it's just this is a random choice of A will exactly be the union bond, that is size of A is F2 to the size of A is QS minus 1 by E power Q power M. E by Q power M is the total fraction of errors. That's this. So therefore, this is a quantity which is strictly smaller than E by Q power M minus S. Okay, that's the one. So as long as if S is very small, this is a small quantity, and you can assume that you have picked up a affine subspace in which there are no errors. So if there are no errors, now you can just interpolate on this and try to extract the polynomial. Just so now you are reduced the same space from N to this S space. You now just read off everything over here except this one particular point. You want to interpolate and read it. Now the question is, you want to interpolate and read. Is there sufficient information? You want to interpolate to obtain a degree R polynomial in R variables, in F variables, and be able to this one. The question is, to interpolate this, you need to know that there is this S is not smaller. For example, if this had been S2 and S were, say, S was some number less than D, I claim that you don't even have enough information to extract all degree D. That is, it should be that what should happen. So once again, what's the setting over here? You are hoping that you'll be lucky enough to land on a affine subspace in which you don't see any errors. But this affine, you want to be able to extract the polynomial correctly. Now, it should be the case that two different polynomials, global polynomials, should not become the same polynomial when you restrict to this affine subspace. If that happens, then you won't be able to distinguish the polynomial. You want to ensure that two degree R polynomials continue to have distance. Or two degree R polynomials actually look different. For example, what I want to say is, if
Don't you need it to be the polynomials with bigger let's say 2 points?
that's all you need. You need that. What we will need is you want to be more likely to interpret. So if S is the conclusion of this is that if S is small enough, then this error is small. In fact, we will choose. Go ahead.
If after I settle the subspace, how do I know that this contains no?
I do not know. So what we will just do is this is a property. This algorithm will work only if E is less than 1/3 Q n minus S. Therefore, the probability that you are, with probability 2/3 you are. So for example, if let's assume I'm going to assume that E for here. E is less than 1/3 Q per m minus S, which is which will be a quantity significantly smaller than delta Q mr by 2. Why is it small? We'll come to that later. Therefore, this is the quantity less than 1/3. Therefore, if you pick an affine subspace, 2/3 of the time you're going to get it correct. You just do it several times over and do a Chernow bound. So at a particular point, you get it correct. But the point is, so if S is small enough, then this error is small. But on the other hand, what you need is, we also need the following fact. We also need, yeah,
S is a dimension of the space.
of the dimensional space. Yes. We also need two different polynomials of degree R. Have distance at least 2 over F2 to the S, F2 to the S. Why do I need distance 2? If I just want two distinct polynomials to remain distinct. So I need some distance. I need non-trivial distance, distance 1. But the point is I'm taking off this one point. So the distance could have happened on this one point, the point which I took. So I need the distance to be elsewhere. So I need the distance. I need to pick F large enough such that a degree R polynomial, distinct degree R polynomials will have distance at least 2. Okay, this is what happened. And you stare at the Schwartz-Zippel Lemma, you see that this is true, provided R is less than S into Q minus 1, strictly smaller than S into Q minus 1, then we can do this. If there are the problem one, you can get it. This will actually go into your fourth problem set, but why this is, that is, well, basically I want to make the following talk. If P1, P2 are P1, P2 belong to F less than or equal to R X1, X2, XS, P1 not equal to P2, and R is less than S times Q minus 1, then the distance of P1, P2 is at least 2. Okay. What does this guarantee to us? That is, this guarantees to us that when you restrict to this S space, no other polynomial restriction could have been the same. What you see here is just unique to this polynomial. Every other polynomial will differ from here in at least one place, in one other place. So you will extract, you will get the value correct. That's all you want to do. So that's the entire algorithm. The algorithm is basically going to be. So this is why I will choose yes. So hence we choose yes to be. Yes to be the ceiling of R plus 1 by Q minus 1. Because this will satisfy. If I choose yes to be that, it satisfies that condition. So you choose yes to be this object. So you pick a random. So the algorithm is basically this. So this the local decoder. This is really a local decoder. Local decoder. You're given F. F to M. F. We are saying there exists a P. That's where delta FP is less than 1/3 Q power n minus S, where S is R plus 1 by Q minus 1. And furthermore, let's assume you're also given a point, you're given a specific point, and this is the input. Algorithm, yes. Pick a random affine space of space A, that kind random affine space of space A of dimension yes, that contains Z. Read F restricted to A, interpolate to obtain the value of p hat. And this algorithm is correct with probability 2/3. Therefore, if you run it repeatedly here, you get it correct. Correct. If you want to get the whole code word correctly, you run for each point, you ensure that the error goes down something smaller than like a one. You repeat this algorithm, say m log q times. Therefore, the error per point is less than say 1/1/10th of 1 over q per m. Therefore, the union bound over all the q per m points, the error, there's any error in over all of them is less than 1/10. Therefore, globally, you have got it correct with probability 9/10, and then you do a global interpolation to get the coefficients if you want. So this extracts each, but every location it extracts easy. Exactly. Yeah.
Even absolute to this, I
Mhm.
don't need to be all important for the state. I think that decoding and doing
You can do over a systematic and you will need not go through the entire thing, except that you don't have to go over the entire thing. But if you want to extract this one, so this is an extreme local decoder in the sense that suppose I just want to read this location, easy, it lets you read off this location. So the advantage of this is it doesn't work all the way up to the half the minimum distance, but it's extremely local. That is, each run of the algorithm reads such a small fraction of the input and is yet able to recover it. Hardly, this is truly local, unlike this one. It's very different from the previous thing. It just reads, each run of the algorithm reads only this affine subspace. The affine subspace is small enough so that you can apply union bound so that the affine subspace is erroneous, but it's large enough so that the two distinct polynomials can have distance at least 2 inches. So there's a tension between these two, and that tension is satisfied if you set yes to be of this value. You had a question. Yes.
So if you wanted, you need me on decoding the H to have been
Not R+1. Actually, so if you stare at this very closely, this curve comes. By the way, that 1/3, this 1/3 is not really an issue. This 1/3 can be made half minus epsilon. And then you boost it, you can boost it. That's not an issue. The question is how do these two differ? How does this S? So if you stare at this a little carefully, so I want to now do remarks on. So we have remarks. On number of errors handled. Let's recall what's the distance of the Reed-Muller code. For that, you have to write R as A into Q minus 1 minus plus B, and then the distance of delta Q MR was, what was it? It was Q minus B into Q power M minus A minus 1. Yeah, that was the distance of the query one. What are we doing here? We are picking S to be equal to R plus 1 by Q minus 1. So here, if you do this, you can notice that this, because of this, you can see, right? So this R satisfies is less than S times Q minus 1. This was a condition that we had. And you can also notice that this, you can now write R is equal to S Q minus 1 minus P, where T is 1 less than or equal to T less than Q minus 1. Yeah. So this will be this. So it's almost, so this expression is almost of that expression, except that this is as a minus sign, and that one. So this is hand. So notice in this language, so we are handling, and the number of errors handled is Q power n minus S by 3. So this is not exactly the decomposition I wanted. There I wanted to write as A q minus 1 plus B. Here I written as S q minus 1 minus T. If you look at this a little carefully, you can show that the distance in this case delta Q and R will actually be T plus 1 into Q power n minus S. You take this expression, convert it to that expression, this will be the response. So notice that's the distance. What we're handling is Q power m minus S by 3 over here. By the way, this 3 can be made like this. Let's assume this is half. This 3, 1 by 3 can be made like 1 by 2 minus epsilon. So the only difference is this extra T plus 1 factor over here. That can be Q. So the distance that is being handled here can be off by a factor of Q from the actual minimum distance. So that's where the whole difference is coming. So in other words, the number of errors handled is certainly lies between. This is a number which lies between the delta Q MR by 3 and by 3Q and delta Q MR by 3. So it's a number lying between these two numbers. So it's this extra factor of Q is what is the problematic. Otherwise, it's pretty good, this one. So for small fields, it's reasonably work. As the field becomes larger and larger, this is the problematic. Okay. Questions? So this is a very local decoder. The reason I said it's not good in some sense. It doesn't handle all the way up unique distance and all of this, but it is we will use it later on in the course. We will use it later on in the course to construct local decoders. We saw this notion of local unique decoding. These things will give you local decoding. Be able to decode the receiver, look at a very few locations, and still be able to do it. How are we doing? Right. I want to. Okay, so both these algorithms you saw, Reed's majority decoder and this one, they had advantages. One worked all the way up to half a minimum distance, other worked for all fields, but they are not satisfactory. They did not answer the whole question. The next way of doing it, we'll reduce the third approach. We'll actually reduction to Reed-Solomon code. This will handle the whole. This is due to Pellikaan-Wu. Actually, very simple but clean reduction. So, and the reduction goes this way. So we are working over this M variate space. Notice we have done, while talking about BCH, we said, in general, we know that there is this isomorphism between this and FQ to the M. And in fact, while talking in the BCH code, we had explicitly stated what this isomorphism is. We did it for Q equals 2, but the same thing actually worked for everything. So in particular, you could come up with this trace function. You could define this trace map, which goes from FQM to FQM, sorry, the large field to the large field, in which Z gets mapped to Z plus Z per Q plus Z per Q square, all the way up to Z per Q per M minus 1. We only did the Q equals Q case, but the exact same proof goes. And we also let eta 1, eta 2, eta M be FQ independent elements in FQM. Then we saw that the mapping which takes an element Z here to sorry, and this is goes to the small field. The trace map will always take you to the small field, and that's easy to see. Just take this to the power q, you get back the same object. Therefore, trace of z to the power q is trace of z. Therefore, the trace of z has to be in the small field. So it's a polynomial map, but yet it maps everything in the large field to the small field. And we saw that this was something which we had already done. Trace eta 1 z, trace eta 2 z, trace eta m z. This is in fact an isomorphism. We had this nice isomorphism. We did all of this when we talked about BCH code. We did it for the specific case q equal to, but nothing in that was actually specific to q. It worked for arbitrary. So let's take this. Let's stare at this. So if you have a polynomial over here, so now what is in the what's the Reed-Muller setting? The Reed-Muller setting, we have a polynomial in of degree less than or equal to r over here. We can now say, how is this polynomial? What is the corresponding polynomial? It's an m-variate polynomial. What is the corresponding polynomial when I view it as a univariate polynomial? Because it's a polynomial on this map. I can think of it also as a polynomial over the large field now, as a function over the large field. What is that function over the large field? So the corresponding polynomial p tilde z is exactly p of trace eta 1 z, trace eta m z. This is the corresponding univariate polynomial that you have here. Is that okay? So given a p here, this is a Reed-Muller code. I'm going to pull it back here to get a p tilde here, which is a univariate polynomial. Notice that this univariate polynomial could cross. So typically, when you talk about Reed-Solomon codes, you never talk of polynomials which shoot the size of the field. So the degree of the polynomial is always smaller than the size of the field. This one, the degree of this guy itself is q power n minus 1. If I add q of them with each other, already if I multiply q of them with each other, they will shoot up. For example, if q is 2, even if I multiply 2 of them against each other, if you go to 2 power n, the degree will go up. So as a polynomial, this polynomial is not one of the Reed-Solomon polynomials which we have been looking at. It's a polynomial of degree larger than the this one. But let's look at some special cases. Let's look at some special cases where this will not happen, or so the one case which I want to look at is r is less than q. The two special cases we handled at the very beginning of the lecture, that the field is very large or the field is 2. If r is less than q, then what is the degree of p tilde? Now,
r times q power n minus 1.
it's just the syntactic degree itself is r times q power m minus 1, because you are at most multiplying r of those. Each guy can get any monomial is going to involve r of these guys. So possibly sometime more than once or so, but any monomial is just involving r of them. Each one of them is of degree q power m minus 1. Therefore, the total degree could have just gone to r times q power m minus 1. And in this case, we know that this is less than q power n, since r is less than q. So this is our Reed-Solomon setting. The degree is this one. And then so now you can use this polynomial p tilde also as a Reed-Solomon code word. What is the degree? What is the distance of the Reed-Solomon code word? Or rather, what is the probability the polynomial becomes 0? It's exactly degree by q. That is just exactly r by q, which is the same thing with Schwartz-Zippel Lemma. Therefore, this polynomial, all I'm claiming is, you have what have I done? I have taken a Reed-Muller code with a particular distance. I've embedded it as part of a Reed-Solomon code with this one, and the Reed-Solomon code also has exactly the same distance. So, in other words, I want to say evaluation of p tilde is a member of Reed-Solomon over the large field evaluated at the large field with degree RQM minus 1. You agree with this? And the distance of this is exactly 1 minus R by Q, which is the distance of the Reed-Muller code. We started off. So what have we done here? I have shown Rm. So for this case, I've shown that RMQMR is a subset of RS FQM RQM minus 1. That is, every Reed-Muller code word is actually also a Reed-Solomon code word in this setting. It is just some subset of a Reed-Solomon code word or happens to be Reed-Muller. So it is that it's a certain special class of subset of code which happen to evaluate to the base field at all points. Now, any problem over here? Why should I now look at it as a Reed-Muller code? I can just look at it as a Reed-Solomon code, do all the algorithms, the decoding algorithms over here, and then just find out if the final thing looks like a Reed-Muller code, do one interpolation. So this sort of tells you that Reed-Muller code, when over the code field, is exactly, in fact, a subcode of the Reed-Solomon code. And importantly, this is and furthermore, the distance is the same. That's important because all our algorithms depended on the distance of the two codes, and I'm saying the distance is not changing in this. The distance is the same. Let's look at the other case when Q equals to. Once again, P tilde of Z was P of trace eta 1Z, trace eta 2Z, trace of eta MZ. So here what I'm going to say is, of course, the polynomial here in this case is going to shoot larger. The degree is going to shoot larger than Z power 2 power m. But you only care about the evaluation. So what you could do is you could just take the mod of this polynomial Z 2 power m minus Z. If I take mod as an evaluation over the large field, nothing changes. So I'll define P tilde Z in this case to be this object. Okay, fair enough. So this is a polynomial. I just forcibly reduce the degree to less than 2 power m so that I can think of it as a Reed-Solomon code. But now let's ask us, I want to ask what is the degree of P tilde? Okay, let's to be a little more this one, let's look at any monomial. Let's look at any monomial before the reduction. Before the reduction, any monomial here, any monomial of P tilde before reduction by mod Z power 2m minus Z is of the form Z 2 power I1 plus 2 power I2 plus 2 power IR. You agree? It's just going to, it's a product of every monomial is, sorry, not IR, IS IK for K less than or equal to R, and each of the IJs being some number between 0 and m minus 1. Because any monomial in the Reed-Muller world looks like anything in the Reed-Muller world is going to just take a product of K guys. It's a product of K guys. And a product of K guys, then if I multiply them, any monomial that I'll get is just going to pick it, it's going to be of this form. It's going to be some 2 power I1, IJs might be the same IJ, I don't care.
So there will be some 2 power I1 plus 2 power I2 all the way up to 2 power Ik for some k less than or equal to R. Now, so all the monomials look like this. Now these monomials, notice that I want to say that I can actually assume the k's are distinct because if two monomials are the same, if I1 and I2 are the same, this is just going to become 2 power I1 plus 1. They will add together, become 2 power I1 plus 1. And in the number of these guys will only k will become even smaller by doing this. Whenever two things are the same, of course it can shoot up, it can go all the way up. The two things 2 power m minus 1 and 2 power m minus 1 can become a 2 power m. But at 2 power m, so now I want to say, now on reduction by mod z 2 power n minus z 2 power m minus z, each such monomial. So you can say, one second, each such monomial becomes of the form z power 2 j1 plus z power 2 j2 plus z power 2, sorry, plus 2 j, say j, some, this is the difference, say jl, where L is less than or equal to R, and the J1, J2, JL are, this is going to be important over here, are distinct, and each Ji is between 0 and minus 1. Why am I going to say? So I take this guy. If there are any two guys that are same, they collapse to this one. The thing is, they can also go to 2 power n. But when they go to 2 power n, it becomes 1, it becomes 2 power 0 because I'm going mod z 2 power m minus z. Once it gets 2 power m, it becomes this one. So I'm going to constantly do this collapse till finally I end up with only distinct bits. R is the original Reed-Muller thing. So I started off with k guys possibly overlapping. And I keep doing this process. The number of guys will only become smaller, and furthermore, at this time, I know that they will all be distinct because they are the same. I have reduced them, and if they ever go to 2 power m, I'll get it back to 1 because of by doing this one. So now you know that after doing the mod, every monomial looks of this form. So what is the largest degree? Hence, degree of P tilde is certainly less than 2 power n minus 1 plus 2 power n minus 2. No, exactly n minus r. There are r there. And what is this? This is 1 plus 2 plus 2 up to 2 power m minus 1 minus 1 plus 2 up to 2 power m minus r. That is exactly 2 power m minus 1 minus 2 power m minus r minus 1. This is 2 power m minus 2 power m minus 1. So no matter what you do, you take this Reed-Muller code, you do this isomorphism map, and then go mod z power 2 power m, you eventually get some P tilde. Now I claim this P tilde that you get this way can never have degree larger than this one, because you started off with the Reed-Muller code of degree r. What is the distance of this Reed-Solomon code? In fact, the maximum number of places, it's exactly 2 power m minus r is its distance, which is the distance of the corresponding Reed-Muller code. So once again, in this case also, in other words, in this case also we have, in this case also, Reed-Muller 2 mr is a subcode of Reed-Solomon over F2m, and now the degree is 2 power m minus 2 power m minus r. And the distances are the same.
We showed this for just the two exchange cases, but this is actually a fact that's true for every single queue. So in fact, I will not do this. In fact, more generally. Take any Reed-Muller code, QMR. It is a subcode of Reed-Solomon, FQM, evaluated at the entire FQM points. And what will the distance be? It will be Q power M minus delta Q. The degree will, this will be the bound of it. So that you exactly get the right. It's, so this is another way of proving that the Reed-Muller code has this distance. Show that it is this one. Here you know it has distance, therefore it has this. So this is a fact that I will leave it with all this. So basically, this last thing says that you don't, Reed-Muller code is always a subcode of Reed-Solomon. So you can inherit all the algorithms for Reed-Solomon for Reed-Muller. If the set of evaluation points is available, it's important the set of evaluation points is available. No. So you take that, that is just to identify, but as an evaluation set, they are, this is a code word, that is a code word. Evaluation, there's the identity map is the as an evaluation, this is an evaluation. It's just that the trace map is all to find out if this is the evaluation, this polynomial, what is the evaluation of which other polynomial it is. To get the two polynomials, you're doing the trace map. For the evaluation map, there is nothing going on in the process. It's the identity map that is doing the inclusion. So it's the inclusion in the identity map. It's just that if you want to find out what this as a bunch of code words is exactly a subset of this as a bunch of code words. So each code word here you are associating with a polynomial. To get to that corresponding polynomial, you are doing all this trace map, and otherwise this is just as a set, it is a subset of this set. And they have the same distance. Yeah.
Many of the points coincide, right?
Which ones?
From the polynomial P.
Yeah.
We are calculating the P, right?
Yes.
So many of the code words under that modulo.
As evaluation points, they cannot coincide. Z power 2 power m minus z. As evaluation, it cannot. It's a that why if something has, they cannot coincide everywhere. They can coincide only at a few locations. Z power 2 power m minus z is you are going mod Z power 2 power m minus z. If two things map to it, they have to be the point is you care about these code words only as evaluation map. You don't care about them as polynomials. And as evaluation map, going mod this does not matter at all because we are anyhow evaluating only on points in 2 power m. So when you go this, nothing changes because this is an identity for points in the field which we have. Yeah. So you might now ask, why do we ever care about Reed-Solomon codes? This is a larger code word space with the same distance and stuff. Now, the reason you care is the alphabet is smaller. The alphabet is smaller. The Reed-Muller has alphabet Q, whereas this has alphabet Q for. So there is a reason sometimes you would prefer the Reed-Muller over this. So if you don't care about the alphabet, obviously you should just go for Reed-Solomon. There's no reason for Reed-Muller. But otherwise, Reed-Muller is one. And this one nicely says that every algorithm for Reed-Solomon you just inherit it for the corresponding Reed-Muller.
So the last calculation for F2 because it 2 power n minus r.
Yeah.
Last calculation, this is not a coincidence. So in the second case just above.
Yeah.
You got this quantity 2 power n minus r.
Okay.
So in the last sentence, it was not a coincidence.
This is not a coincidence. This is not a coincidence at all. In fact, if you carry the proof for this will be the same proof for the Schwartz-Zippel Lemma proof. The proof of these two will go exactly along the same lines. This is not a coincidence at all. But I just want to make one more point. Remember, how did we define BCH codes? BCH codes were those codes, Reed-Solomon, which when evaluated on all points, returned only the base field. Huh? Reed-Muller is also returning the base field. Huh? So Reed-Muller is even more structured. So if you actually look at it this way, there is Reed-Solomon is the super code sitting here. Let's focus our attention on Q being 2. You can define BCH even for Q not 2. We have Reed-Solomon as a super code sitting here. It contains BCH. BCH has all those evaluations of Reed-Solomon which evaluate to points in GF2 on the base case. Among them, there are a few of them which look like degree R polynomials evaluations in this case. So actually, Reed-Muller is a subcode of BCH, is a subcode of Reed-Solomon. This is always the case. Yeah, so the reason I wrote it this way is because the degree parameters for this one I had to choose one myself, this one, so I don't want to. So, but you mean what you say, we know what I mean over here. I choose the Reed-Muller code over here. So this is the Reed, you want to be able to this one. This is RMQMR. So this will be FQ to the M, FQ to the M, and the approximate degree parameter. And BCH is exactly this Reed-Solomon intersection FQ to the M. You just intersect those Reed-Solomon codes which always will give you base field evaluation. Reed-Muller is a special family of those. BCH says it could be that or a little more than that. The point is here I understand the dimension, distance, and everything. Here I don't. This is not trivial. So it's always better to use BCH over the Reed-Muller because they are the same alphabet. They're only better the same distance. It's just that the rate and distance is not something which I know well enough. I don't have the bounds which we get are typically what we get from Reed-Muller code. It's not that I understand the rate of BCH code well enough. There are certain special settings for which we understand. We don't have a nice encoding. So BCH is the intermediate of it. If you look at the point, is slightly smaller, then I get a nice encoding. Stop with that.